Now that we've really got into Poisson processes, there are two applications of them that are worth studying. The first is called the random telegraph signal for historical purposes, and it is one of the useful stochastic processes models that will also be useful in the third module of this course. And the second one is shot noise. So let's talk about the random telegraph signal. Consider a process x of t, which takes values plus minus 1. Going back to the telegram, where telegraph, which had basically two voltage levels. This changes polarity at a random time instance. And these random time instances occur according to a Poisson arrival process. Let's show that if initially this wave starts with plus or minus 1, equiprobably, then it is at any time equally likely to take the values plus or minus 1. It's not that hard if you think about it. It's quite intuitive. But its proof is going to use several things that we have studied in Poisson processes. More importantly, we will compute the covariance of the value of this process at T1 and T2. The value at T1 is a random variable x of T1. The value at T2 is a random variable x of T2. We'll compute the covariance of these two things. And this is going to be the autocovariance function of the process. And we will observe an interesting property, which you will talk more about in the third module of this course. All right. So, let's see. Let's show what values x of t takes. Maybe I want to just draw a sample path. At time 0, this process starts possibly at 1, possibly at -1. Suppose it's at 1. And it's going to change polarity at these instants that occur according to Poisson arrivals. All right, so changes polarity, goes to -1, stays at -1 until the next arrival, at which point it changes again back to 1, and so on. Another kind of sample path could start at -1, of course. Go like this, etc. Okay. Now, what are the inter-arrival times? We know that the inter-arrivals I'm sorry, are exponential. Now, basically, the question asks us to prove that, show that x of t is 1 with probability 1/2. So take any time t, what is the value? Now, probability that x of t is equal to 1 can be written as the probability that x of t is 1 given x of 0 was 1 times 1/2 plus the probability that x of t is 1 given x of 0 is -1 times 1/2. Right? I'm applying total probability theorem. and 1 and minus 1 occur equiprobably. Now, what is this probability? Now, clearly, this will be true if there's an even number of polarity changes from time 0 to t. Do you see that? Because if the polarity does not change, or changes twice, or changes 4 times, I'm going to be going back from 1 to 1. So this is the probability that n of t is even. Similarly, this is the event that x of t is 1 when x of 0 was minus 1. It will happen if there's an odd number of polarity changes. So this is the probability that n of t is odd, which is 1 minus the probability that n of t is even. So if the probability that n of t is even is p, this is 1 minus p. So I have the probability that x of t is 1 being equal to p times a half plus 1 minus p times a half, and that is 1 over 2. Right? You don't even need to compute what the probability that n of t is even is. Thanks to Adam in the other section yesterday, he pointed this out. We don't need to compute what the value of this in order to find out that this is 1/2. But then for the next step, we will probably have to compute it to find the covariance. Any questions so far? Now let's think about the covariance of x of t1 and x of t2. All right, so now what is covariance? What is covariance? This is the expectation of x of t1 minus expectation x of t1, right? Multiplied by x of t2 minus expectation of x of t2. But what is the expectation of t1? Well, we computed in the previous part that at any time x takes the value 1 with probability a half. We computed that this is a half. Right? So x takes plus minus 1 with probability 1/2 each, so the expectation then clearly is 0. So this is 0, this is similarly 0. So then we need to compute simply the expectation of the product x of t1 times x of t2. Right? Okay, but x of t1 times x of t2, how many possible values does this product take? Either they're both 1 or both -1, in which case the product is 1, or one of them is 1 and the other is -1. And so basically this is 1 times the probability that x of t1 is equal to x of t2 minus 1 times the probability that x of T1 is different from x of T2. Do you agree? Because if they're different, the product is -1. I get a -1 contribution. If they're equal, the product is 1. But what is the probability that x of T2 is the same as x of T1? Going back to the same argument, they're equal if there's an even number of polarity changes from T1 to T2. So this is the probability that n of T2 minus T1 is even. And this is basically 1 minus the probability that n of T2 minus T1 is even. So at the end of the day, I couldn't get out of computing the probability that n of T2 minus T1 is even. Let's compute over here the probability that n of tau is even. Well, n of tau is the number of arrivals in a Poisson process, right? So we are summing lambda tau to the k e to the minus lambda tau over k factorial over even k. But I could write this as, if you will, 2k. In terms of 2k, k going from 0 to infinity. So now I'm summing over only even entries in the summation, in the Poisson PMF. Okay. But let's see. But that's not going to really... Let's see if that's going to help. Yeah, it does. I can break this into two Taylor series expansions, the sum of two Taylor series expansions. Think of the Taylor series expansion of e to the, so first of all, let's get e to the lambda tau out of this summation, okay? And then I will write this as k from 0 to infinity lambda tau to the 2k over 2k factorial. Now, this actually is the sum of e to the lambda t plus e to the minus, lambda tau, e to the lambda tau, plus e to the negative lambda tau divided by 2. Because this would bring me negative entries for the odd terms and they would cancel. For the even terms, I have twice this, which I take care of with the 1/2. Right. So that gives me 1 over 2, 1 plus e to the minus 2 lambda tau. That is the probability that there's an odd number of polarity changes in an amount of interval of size tau. Okay. So then let's return to the covariance. The covariance turns out to be 1 times the probability that n of T2 minus T1 equals even minus 1 minus the same thing. So I can express that maybe as maybe twice the probability that n of T2 minus T1 is even minus 1. Am I right? Okay. But I just computed the probability of being even. 1/2 times 1 plus e to the minus 2 lambda times the time difference. So multiply 2 with 1/2 and that's gone. So 1 plus e to the negative 2 lambda, the time difference, T2 minus T1. Minus 1. Wow. So that's gone. That's pretty good. Pretty good. The covariance turns out to be an exponential decay where the decay is increasing with the time difference, meaning as the time difference from T1 to T2 increases, the covariance decays to 0, which makes sense. The dependence from, let's not say dependence, but x of T2 becomes less and less related to x of T1 as time goes on. All right. So you will learn something, a notion called wide sense stationarity in module 3. And this process is going to be an example of that. The covariance, the autocovariance function of this process depends on the time difference between the sample points. Samples become less and less correlated in time. Here, of course, I assumed that T2 is a time that's later than T1. If T1 and T2 were switched, we would have T1 here. In general, for the autocorrelation function, I can substitute this parenthesis with an absolute value clearly because we're subtracting here the bigger one from the smaller one from the bigger one. Okay, so that's the random telegraph signal. The other interesting stochastic process we have related to the Poisson process is shot noise. Now, shot noise is a kind of noise that can occur in some systems, for example, optical communication systems. Consider an impulse train, okay? Where basically it's a sequence of impulses occurring at random times. The times of the impulses are arrival times in a Poisson process, okay, of rate lambda. Let's pass this process, this impulse train, through a linear time invariant system with an impulse response h of t. The resulting filtered process is x of t, okay? And this is known as shot noise. For example, you can think of h of t as the current pulse that occurs resulting from a photon hitting a photodetector, okay? And when you have a sequence of these photons hitting, you're considering the sum of the responses to each. And as one of them is decaying, the other one starts, etc. So you have the sum of pulses. Okay, so what kind of random process is this? Let's try to understand. For example, let's compute its expectation. All right. So I'm going to erase this part while you read the problem statement a little bit more, maybe. Okay. Note that when we take a Poisson process at rate lambda, I can also express it as shot noise, where the pulses would be what? Unit step functions. How about that? U of t minus si. I from 1 to infinity, really. Where n of 0 is 0. Why? Because when I have impulses occurring at S1, S2, this is time 0, this is t. If I pass this impulse train through a filter h of t equals u of t, this is what I get. You already studied this in your signal processing course. When you convolve an impulse with u of t, you get u of t. And you get, when you convolve an impulse placed at S3 with u of t, you get u of t minus S3, for example. So you have these things adding up. As a result, I have these u of t functions, right? Unit step functions adding up to form the n of t counting process. Okay. So then we can think of n of t as the filtered impulse train. Where basically this impulse train, let's call this z of t comes in to the system. The system is just an integrator, in other words, a filter whose impulse response is u of t, and the output is n of t. Okay. Now instead of this, consider, instead of this, another filter, h of t. And that gives us the process x of t, which is summation h of t minus si, I from 1 to infinity. Okay, so for example, if h of t looks like this, z of t, and I'm going to draw it right underneath here. This is n of t, this is z of t. If h of t looks like this, the resulting, I'm not doing a very good job of drawing this, but the resulting shot noise waveform is going to be looking something like this. Okay, so at any time, what is the expectation? Okay. Let's consider, for example, the expectation of z of t. I'm sorry, this is not z of t. This is x of t. X of t is my shot noise process. The expectation of the shot noise process conditioned on n of t is equal to k. The number of arrivals by time t is equal to k. Well, that is the expectation of the summation h t minus si, I from 1 to k, right? Okay. But I can change the order of the summation and the expectation. All of signals and systems is changing about the order of summations and integrations, right? So, somehow I lost the conditioning along the way. But I mean, k is given, so k appears here. So I'm using the conditioning, right? Now, how do I compute this expectation? Well, I mean, here what's random is si. Si is the ith arrival time. Okay, so I'm going to have to think about where the arrival times are located. What is the distribution of arrival times conditioned on a given number of arrivals? And that brings me back to this problem from the previous lecture, where I computed the probability given that there are k arrivals in a time interval, what is the probability that all of those arrivals fall in a given portion of that arrival? And it turned out to be t minus x over t to the k. So that's when you differentiate this and find the PDF of the arrival times, you will observe that the arrivals are occurring uniformly. Okay, so we will use this result. So, let me write it down. Given n of t is equal to k, s1 up to sk, the arrival times are uniformly distributed in 0 to t. So in a Poisson process, given that there are k arrivals in a time interval of size t, they are each uniformly distributed in that interval, which means each point is equally likely to fall anywhere. I'm throwing k points into the interval from 0 to t, and they're equally likely to fall anywhere. Okay. So, we will use that fact to compute this expectation. The expectation of h t minus si equals the integral from 0 to t 1 over t h t minus s ds. What is 1 over t? Each is uniformly distributed from 0 to t, so the probability density function is 1 over t. Okay? So that is 1 over t integral h of u du from 0 to t. Okay? Therefore, the expectation of x of t given n of t is equal to k is this sum of identical terms, k over t, summation, integration, h of u du. Okay. Now, that is the conditional expectation. How about the unconditional expectation of x of t? Expectation of x of t equals expectation of n of t divided by t, integral h of u du. So now this expectation needs to be carried out over so basically this is iterated expectation, right? Expectation of x of t is expectation over n of t, the expectation given n of t. So basically, what is the expectation of n of t? Lambda t. So lambda t over t, integral 0 to t, h of u du, which is lambda integral h of u du. Okay, so we've essentially found out that this expectation of the shot noise process at any time depends on the rate of the impulses as well as the integral of the pulse shape. And that's it. So if this integral is finite, the expectation of the process approaches a constant. Okay? So if the pulse is, if the current pulse, for example, when the photon is the photodetector, has finite duration and integrable, then at any time, if you look at this shot noise process, it has constant expectation. And that depends on the rate of arrivals. Okay, so that essentially completes our discussion of the Poisson process. We have defined the process, examined its properties, solved some basic examples that use those properties, and then studied two sort of continuous time stochastic process models, the random telegraph wave and the shot noise process, that are emerging from the Poisson process. In the next hour, we might do some extensions of these things. So enjoy the rest of